My name is Milo McCard. I am an engineer that's worked at Rivian and Tesla, and today I'm going to show you exactly how to do this challenging shear moment diagram. First, we're going to start out with a free body diagram, and you can see that on the right side of the page. I have these forces in here already, but we also have to do our reactions at A and B. At A, we're going to have a pinned connection, so we're going to have a reaction in the Y, and we're going to have a reaction in the X, and then at B we have a rolling connection, and so we are only going to have a reaction in the Y. Next, we have to figure out like what these guys do right here, because they have this weird L-shaped connection at C and D. And the way we're going to do that, we can see that these are actually offset by a certain distance, and you can see it says 50 millimeters right there. And so that means that there's actually going to be a moment about this point and about this point, and so we have to figure out what that is. And so the way we're going to do that, we're going to come down here and we're going to say the moment at C is equal to 75 newtons times 50 millimeters. And that's going to come out to 3750 Newton millimeters, which equals 3.5 Newton meters. And that's going to be the same at point D as well. Now, after we've gotten those, we're going to have to move on, and we're going to have to find the reactions at A and at B. And we're going to start by doing that with the summation of the forces in the Y direction. We'll set that equal to 0 because this is statics. Everything is going to equal 0 in the summation of forces. After we have that, we're going to say R of A in the Y minus 75, because we have a downward facing vector, minus 75 again, plus RB in the Y. Right now we only have one equation, but we have two unknowns, and so we're going to have to figure out a way to get a second equation to solve for one of these unknowns and then move on. And we can do that by doing the sum of the moments about point A, and we can use that to solve for RB. And so again, we're setting it equal to 0. And so this 75 right here is acting on this beam at this point. And so what we're going to do, this first moment is going to be negative 75. That's because it's going to cause a clockwise rotation times 250 millimeters. And we're using 250 instead of 50 because we're doing it from point A. We're not doing it from point C. We're going to have that again, the 75, but this time instead of 250, it'll be 500 millimeters. And then we're going to have plus RB in the Y, and this is going to be 750 millimeters from point A. You might be inclined to stop right here, but we can't do that because we actually have two additional moments that we have to sum right there. And you can see that these are going to be counterclockwise, and so we're going to actually add these to our equation. And so we're going to do plus, what was it? It was 3,500 Newton millimeters, and then it's going to be the same value again because both of those create the same moment. And now we're going to do a little bit of algebra. We're going to say RB in the Y times 750 millimeters is equal to minus 75 times 250 minus 75 times 500 plus, excuse me, these are going to be plus, this one's going to be minus 7,000, and that's just me adding these two guys together. So after we move this over, we're going to get RB in the Y is equal to 75 times 250 plus 75 times 500 minus 7,000, all divided by 750. And so this is going to come out to equal 65.67. And the reason we were doing this was to solve for equilibrium, but we also needed to eliminate one of our unknowns. And so we're going to take this guy and we're going to plug it back into this equation right here. And so if we go over to the right, we're going to say R A in the y minus 75 plus 65.67 equals 0. Rearrange it, do some algebra, and RA in the y is going to come out to 84.33. And so now we've done equilibrium in the y. I skipped the step, but this RA in the x direction is just going to equal to 0 because there's no other force in the x direction. And so now we can come over here, we can redraw our free body diagram. And then anywhere something interesting happens, there's a new force being drawn, I'm going to draw a dotted vertical line. And that's going to signal to me that there's going to be some sort of discontinuity. All right, now that we have that drawn, I'm going to switch back to red, and we're going to start putting our shear forces in here. And so at this location right here, we have that reaction at A in the y direction, and it actually is going to be equal to this guy right here that we just solved for. And so we're going to go vertically in the positive direction, and that's going to be 84.33. And then we're going to come to the right, and then at this location, at point C, we have a downward force of 75. And then 84 minus 75 is going to come out to 9.3. And so we're going to go all the way down, and this value is going to be 9.3 all the way across. And then at point D right here, we have another negative 75 drop. And so we're going to take 75 away again, and we're going to end up going all the way down to negative 65.66. And so we're just going to keep that value all the way across the graph, and then we're going to jump up because we have this value right there, which happens to be 65.66, 65.67. It's the same thing. Either way, it gets us back to 0, and so we know that this shear diagram is going to be valid. Next up, we're going to draw our moment diagram. And in order to figure out how we draw our moment diagram, we have to take all the areas right here, and we have to figure out what they are. And the way we're going to do that, we're going to multiply the shear value that we have on each of them, so that's going to be the 84.3, 9.3, and the 65.6 by the amount of area that they act over. And so that's just going to be this distance right there. Alright, so now that we have all those values figured out, what we have to do is we have to go over to the moment diagram and we have to draw those in. But we have to figure out what type of line we're going to do on this moment diagram, right? Because up here, we just have this flat line that goes, but it's also possible that we have something linear, quadratic, cubic, so we have to figure out which one we're going to do. There's an order that you have to stick to when you're doing these, and so if you have a constant line on the shear diagram, that means you're going to have something linear on the moment diagram. And so I'm going to draw this point in here, and that's going to be the value that we got from that first area. And so that's going to be 21,082.5 Newton millimeters. And because this is constant up here, we're going to draw this in as a linear line, just like that. And this value, like I said, is going to be that 21,082.5. And then now we have this second area in here. And it's the same story. We have that constant line, and so that's going to end up being linear for us. And so we're going to do that 21,000 value plus 2,332.5. And that's going to take us up to 23,415, just like that. And then we have to go down this value, 16,415. So roughly there, and that value ends up being 7,000. And you'll notice this isn't 0, and that's because we didn't account for these two external moments that we have right there. But if you'll recall, when we were doing the sum of our moments over here, we ended up having a negative 7,000 value. And so this is going to take us back down all the way to 0. And the reason that's a negative 7,000 value is because these guys right here, they're positive, right? Because they're going counterclockwise, and counterclockwise is positive. But when we're doing our shear moment diagrams, any external moment like you have right here, we reverse the sign. And so they're positive here, but here they're negative. And that's this whole problem done.